Hey YouTube, this is my first video in a module that I'm doing on the sum and difference formulas that we often see in trig classes here. But these sum and difference formulas, basically what I'd like to do is introduce everybody to what they look like and kind of how you would remember them, but also talk about how they are useful, and especially we're going to emphasize how we use them to, say, evaluate trig functions for angles that we don't often see values for on the unit circle. So for instance, the sine of 15 degrees, something like that. Don't have 15 degrees on the unit circle, but perhaps we could express 15 degrees as a sum or a difference of, say, two angles that we know some values for. So let's go ahead and start by taking a look at what these formulas are and how we might remember them. So starting with what they are, we just say that they're really kind of a way of saying that if we had a sine, cosine, or tangent function of the sum of two angles or the difference of two angles, how we might be able to re-express that in a way such that we could maybe rewrite it and work with just the individual angles themselves. So sine of A and cosine of B, or cosine of A, sine of B, instead of A minus B or A plus B. We can just leave it as A's and B's. And so pretty convenient when we evaluate some things. Go ahead and take a look at these sum formulas here, and then we'll talk about how they compare to differences. So starting with the sine, we have sine of the sum of two things in the entire angle here. So basically we have two individual angles. This could be like say a 30 degree plus a 45 degree, two things that I know some values for on the unit circle. And adding those together, we might have something like the sine of 75 degrees. Now I don't want to pursue that here, but basically what I want to say is, given the sum of these two angles here, what we could do is we could re-express this entire expression here really as the sine of A times the cosine of B plus the cosine of A times the sine of B. And so what I want you basically to see here is this, with respect to the sine of A and B stay consistent when we rewrite this over here. And this is going to be true for our difference of sines here. We say sine of A minus B, here we have sine A cosine B, cosine A sine B. But what we can do is re-express it as just trig functions of these individual angles. Now with respect to how these are arranged, you'll notice that sine, when we rewrite it, we say it goes sine, cosine, cosine, sine. And so therefore across this, either this sum or this difference, sine alternates. Whereas where we haven't looked at cosine yet, we can look at it now. We can see a cosine A plus B. You get a cosine, cosine, sine, sine kind of arrangement here. And so this is true always with cosine. One thing that I basically want to mention right off the bat is this. If you're taking a sine, sum, or difference formula here, basically when you rewrite it, you're going to start by writing a sine first. And just remember that sine alternates. And then when you rewrite a cosine function here, cosine of A plus B or A minus B, it's going to start off with a cosine here or a cosine here. And just remembering that cosine doesn't alternate, we get cosine, cosine, sine, sine, where this A and B kind of stays in that order throughout both of those terms there. So the only other thing we need to mention here is basically that when you talk about, say, with respect to sine and cosine here at least, the sine, when you rewrite it here, we say, it's a sine here, it starts with the sine here, and sine alternates. We have sine, cosine, cosine, sine. And when we have a plus here, we'll also have a plus here. As a matter of fact, when we have a difference here, we always have a difference here. So it is very much the truth that sine, whether this is a sum or a difference in the initial angle here, that will tell us whether or not we'll have a sum or a difference when we rewrite it. Whereas cosine, when you notice cosine here, we have cosine of A plus B. We get cosine, cosine, sine, sine. Cosine doesn't alternate, and it starts with the cosine here. But you'll notice that this was a positive, therefore we have a difference over here. And if this is a difference here, we get a sum over here. And so cosine is backwards. So some things we want to write here. We would say that when rewriting, the expression on the right-hand side begins with the same trig function as is on the left, as is on the left-hand side. And so this is pretty much always true, and it's going to be true with the tangents down here. We've just been looking at sine and cosine. So that's one thing we notice here. And with respect to also these formulas here, we could say that the order of A and B stays consistent. And that is to say, when we look at the expression on the left here, we have two angles A and B that we're either adding or subtracting together to make the whole angle. but over here we have an A and a B and an A and a B, and we have an A and a B and an A and a B, and even with the tangent, it's got A, B, A, B. So those stay consistent. And then the last thing I want to mention here is this third thing here is the sign of expression on the right-hand side. You know, it's going to matter. So if we say that this is a sine function, we're going to say is the same as on the left-hand side. And if it is a cosine function, it is opposite as on the left-hand side. And that's just saying that if you have, you know, a sum here with sine, it's a sum here, and a difference here, it's a difference. It's the same. But with cosine, it's the opposite. You know, we get a sum here, difference here, sum here. So the only other thing we want to mention here is our tangent sum and difference formulas. And what you're going to see here is that tangent, with respect to what you see, whether it's a sum or a difference, these look pretty consistent. And that is to say that we have A and B with respect to our angles here. And that also on the top, on either of these, we have the tangent of the first, you know, a term in this sum plus the tangent of the second term in this sum here. But we have tangent A plus tangent B, or tangent A minus tangent B. And what you're going to notice is that those signs are the same, you know, with respect to tangent there. So the sum of the tangents, same. I want to write the same, but I'm thinking tangent. Okay, so we have the sum of the difference of the two tangents of the angles. And then on the bottom we have 1 minus or 1 plus the product of these two values here. And you notice that it stays, you know, tangent A, tangent B, but it's either 1 minus or 1 plus. And what you're going to see is that this is always opposite of whatever's on the top. So the top's the same as what's on the left, and the bottom's opposite of what you see on the top, opposite. So what I want to do is I want to put these to use and actually just show you, you know, firsthand here is, you know, what we use these for. And so basically what I've got is a couple of trig functions that I want to evaluate here. We say sine of 15 degrees and then also the tangent of 7 pi 12ths. Both angles that we don't often see values for on the unit circle. You know, we only usually see things that have reference angles of 30, 45, or 60, or they land on a quadrant, you know, when we talk about common reference angles. But with respect to these, you know, 15 degrees, let's see if it'll let me draw on here. 15 degrees would be half of a 30-degree angle here. And so we don't know the values on the unit circle for this. And so what we're going to do is we're going to ask ourselves, you know, is there any other way that we could express the sine of 15 degrees as perhaps the sum or the difference of two of the angles for which we do know some values for, like these two? And the only reason I say these two is because what I recognize is that 15 degrees, what we can look at that as is 45 degrees, which I know values for, minus 30 degrees, which I know values for. And so what we're going to do is we're going to re-express this as instead 45 degrees minus 30 degrees. And all of a sudden, what you're seeing is a situation where we have something like an A and a B, and we can rewrite this using our sum and difference formulas. And that's precisely what I want to do here. And so let's go ahead and recognize this here. We're going to say sine of 15 degrees is really the sine of 45 degrees minus 30 degrees here. And we really do want to explicitly recognize what our A and our B are. So we say A is 45 degrees. Our B in this case is 30 degrees. I'm going to put this in a little index on the left because what we're going to do now is we're going to rewrite this. And recall that when we rewrite this, we have A and B. It starts with the sign on the right since it started with the sign on the left. And because our order of angles stays the same here, we're going to have sine of A. And remembering that sine alternates, we have cosine of B. So we have sine A, cosine B. And I'm just going to fill these in here. We have 45 degrees and 30 degrees. Now, sine of A, cosine B, what we need to follow this up with is either a plus or minus here. In this case, it's a minus because recall that sine keeps the same SIGN sign. And then what we're going to get over here is because it's alternating a cosine sine. So we have sine, cosine, cosine, sine. And we're still going to fill these angles in 45 degrees and 30 degrees respectively. My favorite part about this is all of these are things that we can evaluate because we know, you know, angles that have such reference angles as 30s, 45s, and 60s. So looking at this first thing here, we say the sine of 45. Well, obviously the sine of 45, here's our 45-degree rotation. There's our sine value. So we have root 2 over 2. What I'm going to do is I'm just going to straight up substitute root 2 over 2 for the value of this, because that's what they are. They're, you know, same thing. Cosine of 30 degrees, looking at 30-degree rotation right here, our cosine is root 3 over 2. So we're going to get root 3 over 2 here, root 3 over 2, and then we're going to say minus. Now, minus cosine 45 sine of 30 degrees. I'm just going to fill this in here. Cosine of 45 degrees is root 2 over 2, so we'll get out my teal marker here, teal color. And then we'd say sine of 30 degrees. Sine of 30 degrees is a half. And so evaluating this, okay, so we have some simplification to do, but let me show you this. We say the square root of 2 times the square root of 3 is the square root of 6, square root of 2 times 3, and then over 2 times 2 we get over 4, and then over here we're going to get minus the square root of 2 times 1 is the square root of 2, and this is all over 4. Essentially, in the end, what we get is the square root of 6 minus the square root of 2 all over 4. And you might think this is a wacky answer, but we're going to write something on this because this is a fabulous answer. Oops, I did not mean to do that here. Let me see if I can zoom out. Zoom out. Try again here. So zooming out, let me get my pen tool. Let's see if I can try this again here. Sorry for the wait here. Zoom. Okay, so now I'm going to get my pen tool out and hopefully scroll over to here, and yikes, kind of lost some things here, didn't we? Well, I suppose that what we want to do is this. We had the square root of 6 minus the square root of 2. I can write over here. The square root of 2, and this was all over 4, and this was equal to the sine of 15 degrees right here. And so apologies for the long wait there. What I want to do is essentially this. If you have a calculator, let's go ahead and turn this on, and I want to make sure we're in degrees here. But if we type in the degrees, so I'm in radians, we got to click over to degrees. But if we type in the sine of 15 degrees, we're going to get a decimal here. And I say we get this decimal right here. What I'm going to do now is I'm going to type in now the square root of 6 minus the square root of 2. And all of that, I'm going to take that and I'm going to divide it by 4. And the fabulous thing here is essentially this. You get the same thing. You're like, oh, okay, well, why would I want to do this if I got a calculator? I can just type in sine of 15 degrees, which, you know, way awesome. You can do this, but what I want to kind of essentially point out here is this, that this is what we're going to refer to as the exact value. This is the exact value, and this is what you're going to have to find a lot of the time, okay? So sine of 15 degrees, we're able to re-express that as a difference of two of these angles that we know over here. Now, the one that we didn't get to fill out here, and I don't even think that we'll be able to see it anymore because I'm not really sure what I did to the canvas here, but I believe I was asking for the tangent of 7 pi 12ths, and that's what I want to look for now. Yes, the tangent of 7 pi 12ths. So I'm going to have to write on this canvas here, and you're going to have to bear with me, but the tangent of 7 pi 12ths. The first thing I want to suggest is that we're going to convert this to degrees, 2 degrees. And I have no problem with working in radians here, and we can certainly do that. But the reason why I mention this is because it's a lot easier to do sums and differences without fractions. And so we say if we take this times 180 degrees over pi, then we certainly get our pi radians to cancel out here. And with respect to 12 and 180, I believe that 12 goes into itself once, and if I'm not mistaken here, 12 times 15 is 180. And so we'd say this is 15 degrees. So 7 times 15 be 70 plus another 35. This is 105 degrees. And so what I'm going to do is I'm going to initially rewrite this as the tangent of 105 degrees. And as we assess the situation, really what we're going to be asking is this. What two angles up here that I know values for could I either add or subtract in order to compose 105 degrees? And you might recognize that maybe, what if we took a 60 and a 45 and we added those together? You know, I know values for 60, I know values for a 45. So what we're going to do is we're going to rewrite this as the tangent of 60 plus 45. And a fun exercise here, and I know what you're thinking is, yeah, really fun, is to do this with a 45 plus a 60 and see that you get the same answer here. So what I'm going to do is I'm going to use our sum and difference formula for our tangent here. And so remembering that we get on top the tangent of the first angle, plus or minus, and in this case it's going to be a plus because this is a plus here, the tangent of the second angle, and this is all over 1 either minus or plus, and in this case it's going to have to be a minus because the top is a plus and we are opposite on the bottom, and then 1 minus the product of these two things. So this is a tangent here as well. And so I'm going to fill these in here. We say our two angles are 60 degrees and 45 degrees. We're going to have to look up some values here. But the nice thing is this is truly the answer right here. We just need to evaluate it. And so on top what we get is this, the tangent of 60. Now the tangent of 60, if you know your tangents, is the square root of 3. So we get the square root of 3, so our tangent of 60 here. And our tangent of 45 is 1. So we have square root of 3 minus 1. And on the bottom we get 1 minus, now we have the product of these two, and the tangent of 60, remember the tangent of 60 is still the square root of 3, just like we get on top, and the tangent of 45 is 1. So on the top, you know, I'm gonna have to kind of pull this up here, but we get the square root of 3 minus 1, and this is going to be 1 minus the square root of 3 times 1, which is the square root of 3. And what I want to indicate here is that this is precisely the tangent of 7 pi 12ths. And you could check this on your calculator, but I'm going to tell you that this is what we get as an exact value. So your task now is to try to get some values for the sine of 75 and the tangent of pi 12ths. Keep in mind you'll want to convert this to degrees first, and also think of what two angles on the unit circle that we know values for could we add or subtract together to get these individual angles like 75 degrees. Cheers.